Greetings. Welcome to the AATRN Topological Complexity Seminar, our last one of 2023. Our speaker today is Amit Paul from Queen Mary, who will talk about sequential parametrized topological complexity of sphere bundles. Take it away.
Okay, thanks Daniel for this introduction. So I'm sharing my screen.
Yeah, it's good.
Is visible, right?
Yes.
Okay. So my talk is on sequential parametrized topological complexity of sphere bundle, and this is a joint work with Professor Michael Farber. To define topological complexity, first I will recall sectional category of a fibration. We consider a fibration P E to B, and the sectional category of P is the minimum number K such that we can cover this base space by K plus 1 open set, and on each open set we have a continuous section Si of P. And if we have no finite K, then we say that the sectional category of this P is infinity. So we have this we have a lemma called Schwarz lemma. We will use this lemma later. This lemma says that if we have a fibration P, and if we consider the cohomology group of E and B with coefficient ring R, then we can say that if there exist K cohomology classes U1, U2, UK belongs to the kernel of this P star such that their cup product is non-zero, then we can say that the sectional category of this fibration is greater than equal K. That is the sectional category of this fibration is always greater than equal cup length of kernel of P star. We will use this result later. So now we will define topological complexity. Here we consider a path-connected space, path-connected topological space X, and we consider the path space. It is denoted by Px or x power I. This is our path space, and we consider the fibration Px to x cross x, which is defined by this equation, where each path projected to initial point and final point. And Michael Farber defined topological complexity as the sectional category of this P. The topological complexity of X is the sectional category of this P. And we have some examples, well-known example. If X is contractible, then topological complexity of X is 0, and vice versa. And if we consider the circle, then the topological complexity is 1. Since this circle is non-contractible, so it will be greater than 0. And here we construct two open set, U0 and U1, where U0 is the pair of point from the circle such that they are not antipodal, and U1 is the pair of distinct point. And we define a section on U0 and another section on U1 of our the fibration P, where A0 is the where A0 takes any pair of point XY to the shortest arc from X to Y, and for S1 we consider the anti-clockwise path joining A, X and Y. Here we can take also clockwise path for S1 this section. And we have also another well-known result that this example that the topological complexity of n-dimensional sphere is 1 if n is odd, and it is 2 if n is even. Now here I will recall the sequential topological complexity. For Rth sequential topological complexity. For this, we will choose sequence of R point, sequence of strictly increasing R point from the unit interval. Sequence of strictly increasing R point from the unit interval. And we consider the path space of X, and we consider the R times Cartesian product of X. And this is our evolution move, where any path evaluated at these points, T1, T2, Tr. And thus, RS sequential topological complexity is defined to be the sectional category of this vibration, And it is clear that if we consider R is 2, then it is our usual topological complexity. And we have some useful result that X is contractible even only if every TCR, every RF topological complexity is 0 for any R greater than equal to. And for any R greater than equal to, this topological RF topological complexity is homotopy invariant. And if we consider this sequence on R over R, then sequence will be non-decreasing sequence. So this is also one known example that topological complexity of n-dimensional sphere, RF topological complexity of n-dimensional sphere is R minus 1 if n is odd, and it is R if n is even. For many of the spaces, it is difficult to compute the topological complexity. That's why we give some lower bound and upper bound. Here we have a lower bound and upper bound using LS category of the space. So the RF sequential topological complexity of X is always bounded above by the LS category of X power R, and it is bounded below by the LS category of X power R minus 1. And we have another upper bound using the dimension of X and the connectivity of X. This gives an upper bound for RS sequential topological complexity. And we will have another lower bound using cohomology. Here we consider this diagram, where this is our path space, and this is R times Cartesian product of X, and this is our evolution map, and we consider this is the diagonal map, and this C is the map which takes every element to the constant path at that element. We can see that this is homotopy equivalence. This C is homotopy equivalence. So we can say that the kernel of this delta star is equals to the kernel of this E star. So next we use that Schwarz lemma, and we will give a lower bound for the topological complexity. So using Schwarz lemma, we can say that if we get K cohomology classes which are belongs to the kernel of delta star, such that their cup product is non-zero, then we can say that the RF topological complexity is greater than or equal K. Now we are going to define parametrized topological complexity. So recently, Michael Farber, Jan Cohen, and Weinberger introduced parametrized topological complexity, and it is more universal and flexible, and it is depends on some set of parameter. That means if we give a means it is depends on some parameter set, which is we denote this set by B. So for each B we have a configuration space. For each P belongs to B, we have a configuration space. So we can represent this situation by a vibration like this. So for each P we have a fiber. So that will be our configuration space, and this parameter should be the input of this to get a algorithm. And I'm here defining directly a sequential parametrized topological complexity. So for this, we consider a Woolrich vibration P E to B, and we consider this space EIB, which is a subspace of the path space of E, and it is the collection of paths which are lies in a single fiber. That means if a path alpha belongs to this space, then this composition should be constant. This composition should be a constant. And we consider this space ERB, which are the collection of R tuple from E, which are belongs to the single fiber. That means same fiber. They are all belongs to same fiber. That means if we project these points, then they are going to same point on B. So here also we consider R point from the unit interval, which are strictly increasing, and we consider this map where each alpha evaluated at this T1, T2, and TR. And we define the RS sequential parametrized topological complexity is the sectional category of this pi R. Now, it is easy to check that if we take a subset B dash of B, and if we take the induced vibration on B dash, then we can say that the parametrized topological complexity of the new vibration is bounded above by the parametrized topological complexity of the old vibration. And in particular case, if we choose B dash is a single point, then we can say that this becomes the user topological complexity of the fiber. So we can say this result. That means the parametrized topological complexity of a vibration is always greater than or equal the user topological complexity of the fiber. And this is also a simple example that if we take a trivial vibration, then its parametrized topological complexity is the user topological complexity of the fiber. So in this case, we can say that the total space can be represented as Cartesian product of B and base space and the fiber. So from this on, we get that this space ERB can be represented by B Cartesian product of B and the x power R, and this space EIB can be represented like that. And our vibration pi R can be represented by these maps, where first one is the identity map and second one is our evolution map ER. So from here we can say that the sectional category of this pi R is equals to sectional category of this product map. So sectional category of this product map is nothing but the topological complexity, RF topological complexity of X. So we get this result that for trivial vibration, it will nothing but the user topological complexity of the fiber. So next, it is also a well-known result for user topological complexity. The second one is a well-known result. So if we have a principal fiber bundle, principal bundle with connected topological group G as a fiber, then we can say that the parametrized topological complexity is nothing but the user topological complexity of that group. So here I gives a little bit hint of this group. If we see this diagram, This is P0x is the base path space over G, where each path started from the identity element, and this is the space, and this map is our the vibration pi r, and we can say that this F and F dash, these both are homeomorphism. These both are homeomorphism, and this diagram will commute. And this map pi r dash is projected to the point T2, T3, TR, T2, T3, TR, not on T1, T2, T3, TR. So from this diagram, we can say that sectional category of this this vibration is equals to sectional category of this product vibration. And the sectional category of this product vibration is nothing but the LS category of GR minus 1. So we get the first equality, and the second equality is well-known result for Euler topological complexity. So using this result, we can say that for the Hopf vibration, the parametrized topological complexity of the Hopf vibration is R minus 1. Basically, it is Euler topological complexity of the circle, and the RF Euler topological complexity of circle is R minus 1. So we get this one. And this parametrized topological complexity has some properties. We can say that it is fiber-wise homotopy invariant. In our Euler topological complexity, they are homotopy invariant, but in this case, they are fiber-wise homotopy invariant. That means if we have two vibration on same base space, and if we have a fiber-wise map F from E to E dash and G from E dash to E, so that this composition, this G composite is homotopic to identity map on E, then we can say that this parametrized topological complexity of this map P is less than equal the parametrized topological complexity of P dash. And if these two are fiber-wise homotopy invariant, fiber-wise homotopy equivalence, then we can say that these two are equal. These two numbers are equal. And this is the result for the product of two vibration. If we take two vibration, P1 and P2, where P1 is from E1 to B2 and P2 is from E2 to B2, then if we consider the parametrized topological complexity of the product vibration, then it is bounded above by the summation of parametrized topological complexity of each vibration, their sum. And the second one says that if we have two vibration over same base space, and if we consider a new vibration where total space of the new vibration P is the fiber-wise product of E1 and E2, then we can say that the parametrized topological complexity of this new vibration is bounded by the summation of these two topological complexity, these two parametrized topological complexity. So here, basically here we use this result, means number one, the first result. By first result, we can say that this parametrized topological complexity is parametrized topological complexity of the product vibration is bounded above by this number, and we can see that the product vibration is base space of this product vibration is nothing but B cross B. And if we consider the diagonal of B cross B, then we will get this vibration. if we consider the induced vibration on diagonal, then we will get this vibration. And using our previous result, we can say this parametrized topological complexity is less than equal parametrized topological complexity of P1 cross P2. And by the first result, this is bounded above by this two. And as the usual topological complexity, this sequence also a non-decreasing sequence. And this gives a upper bound for parameterized topological complexity. See, here we have dimension of x using dimension of x and dimension of b, and k is the connectivity of x. That means k is the connectivity of the fiber, and this gives a upper bound, and this is very useful upper bound. And the next we construct another lower bound for parameterized topological complexity. So as usual topological complexity, we consider this diagram, and we consider this map or pi r, and this is our diagonal map, and this is the constant path at if we take x belongs to E, then C of x is the constant path at x, and since it is homotopy equivalence, so we get a similar result at usual topological complexity, that kernel of pi star is equals to kernel of delta star. So using this and Schwarz lemma, we can say that the parameterized topological complexity is bounded by this number k, where k is the maximum number such that there exist k cohomology classes belongs to kernel of delta star, and the product of these cohomology classes is non-zero. That means parameterized topological complexity of P is bigger than cup length of the kernel of delta star. Now we estimate parameterized topological complexity of sphere boundary. Here we consider xi be a sphere bundle, xi be a locally trivial vector bundle of rank q, and we assume that it has a matrix structure. So we can construct associated sphere bundle with this chi. The fiber of this associated sphere bundle will be q minus one dimensional sphere. Since this is q dimensional vector bundle, this will be q minus one dimensional sphere bundle. Then we want to estimate this number, the parameterized topological complexity of this chi dot. Chi dot is our sphere bundle, which is from E dot to B dot. We denote it by this notation. So here we denote E double dot is the pair of point E and E dash, which belongs to single fiber and which are perpendicular to each other. That means they are projected to same point at B, and E and E dash are perpendicular to each other. So we define another fibration which is denoted by chi double dot, which is from this E double dot to E dot. E dot is our total space of the sphere bundle, and E double dot is our new space, this new space. And it is the projection to the first vector, basically. It is projection to the first vector. Now we can see that if we consider the fiber, then it will be q minus two dimensional sphere. Since E and E dash, they are perpendicular to each other, so if you take any element E belongs to E dot, then the fiber will be the q minus two dimensional sphere. And we give a upper bound using this J double dot, and also give a lower bound using this J double dot. So we compute an upper bound for parameterized topological complexity of this sphere bundle, which are given by this number. The sectional category of this J double dot plus R minus 1. The Rth sequential parameterized topological complexity of this sphere bundle is bounded above by the sectional category of J double dot plus R minus 1. And we see that if a vector bundle admits a complex structure, then we can say that the parameterized topological complexity of the associated sphere bundle is R minus 1. Basically, here this number, this sectional category will be 0, because of since this admits a complex structure, so we can define a section. We can define a section from E dot to E double dot, where where the section is where S of E is the E comma root over minus 1 of E. We multiply by this number minus 1, root over minus 1, and this will give a continuous section of this J double dot. So you can say this is 0. So using this upper bound, we can say the parameterized topological complexity is bounded above by R minus 1. And we also know that the parameterized topological complexity is always bigger than the usual topological complexity of the fiber. So here our fiber is SQ minus 1. Since Q is even dimensional, since it has a complex structure, Q is even dimensional. So SQ minus 1 should be odd dimensional, and we know that it is R minus 1. So we have R minus 1 as lower bound and upper bound both. So you can say this parameterized topological complexity is R minus 1 of this sphere bundle. And here we assume that the vector bundle Xi can be written as can be Whitney sum of two vector bundles Xi1 and Xi2. We assume that this is Whitney sum of two vector bundles Xi1 and Xi2. Then we can say that the sectional category of Xi double dots is less than equal the sectional category of this Xi dot plus sectional category of Xi2 dot plus 1. That means the sectional category of Xi double dot is bounded above by the sectional category of this sphere bundle associated with Xi1 dot Xi1 and the sphere bundle associated with Xi2 plus 1. So using this upper bound, and using this result, we can say that the parameterized topological complexity of this vector bundle of the sphere bundle associated with the vector bundle Xi is bounded by these numbers K1 and K2 plus R, where K1 is this number and K2 is this number, and R is comes from this number R minus 1. And from here we can say that if one of this Xi1 and Xi2 is trivial line bundle like this, if Xi is a Whitney sum of eta and eta is a some vector bundle, and this is a trivial line bundle, then we can say that the parameterized topological complexity is bounded above by this number, the sectional category of P dot plus R. And if we have if Xi admits two non-vanishing linearly independent sections, then we can say that this number is less than equal R, because in that case this both number will be 0. This K1 and K2 will be 0. This K1 and K2 will be 0, and we get this is bounded above by R. And if we assume that Q is odd, then then it is actually it is basically R, because of if Q is odd, then SQ minus 1 is even dimensional sphere, and we know that this parameterized topological complexity is bounded below by this number, and this is basically R. And we get that if Q is odd, then this is R. If Q is odd and I admits two non-vanishing linearly independent section, then this is R, and otherwise it is less than equal R. Now we give a lower bound using Euler characteristic class. Here we assume that xi is oriented vector bundle of rank Q, and we consider the sphere bundle associated with xi, and E double dot has the same space we defined previously. It is the pair of point, so that they are belongs to same fiber and they are perpendicular to each other. And we consider this vibration xi double dot, which are projected to first coordinate. Here we actually want to estimate cup length of this kernel. Basically, we know that this cup length of this kernel, the parametric topological complexity is bigger than the cup length of this kernel. So here we estimate the cup length of this kernel. So cup length of this kernel of delta star. So here the result is the cup length of this delta star is equals to the height of the Euler class of xi double dot plus r minus 1, where height means height of Euler class of xi double dot means the largest number k, such that the kth power of this Euler class is non-zero, the largest number k. And using the previous result, we can say that the parametric topological complexity of this sphere bundle is bounded below by this number. So we get a lower bound and upper bound. Lower bound using Euler characteristic class, height of the Euler characteristic class, and upper bound using the sectional category of this xi double dot. And we have a special case when these two numbers as empty. That means height of this number, height of this Euler class is equals to the sectional category of this vibration. So if we assume the dimension of B is less than equal Q minus 1 times height of this Euler class, then we can say that this parametric topological complexity is equals to these numbers, where Q is the rank of this vector bundle. To prove this, here we use this result. That means this one, which state that if eta is a orientable vector bundle of dimension q dash, and the base space b dash has dimension, the dimension of base space b dash satisfies this inequality, then we can say that the sectional category of this eta dot is equals to the height of the Euler class of this eta dot. So using this result, we can prove this one. So here I am giving some hint for the proof. So if we consider the vector bundle zeta, where eta, we know this eta dot, e dot is the total space of the associated sphere bundle, and e zeta is the pair of point where e belongs to the e dot and e dash belongs to the e total space of our original bundle, and it is the total space of the sphere bundle, and they are perpendicular to each other. And we take the fiber wise product. That means this element belongs to same fiber of xi, and we say that this is zeta is the projection to the first vector. So then we can say that zeta is Q minus one-dimensional vector bundle. See, if we take a point, and if we take inverse image of that point, it will be Q minus one-dimensional vector bundle, Q minus one-dimensional vector space. And we can say that the associated sphere bundle of this zeta is nothing but this chi double dot. So this chi double dot. Now, if we check if we consider the dimension of the base space of this bundle, chi double dot, then it will satisfy this inequality. That means dimension of P dot is less than equal dimension of B plus dimension of the fiber, and dimension of P is given by this inequality. So we use this one and we get this inequality. So now if we apply this result on this zeta, then we will get that the sectional category of chi double dot is nothing but the height of the Euler class of chi double dot. And using this one, we get these two are equal. So we get this number is equals to the upper bound and lower bound. This one. Okay. Next, we have another lower bound where we assume that chi is the Whitney sum of eta and the trivial line bundle, where eta is the oriented Q minus one-dimensional vector bundle. Then we can say that the sequential parametrized topological complexity is bigger than the height of this Euler class of this bundle eta plus or minus 1. And in particular, if we consider this dimension of zeta is odd, dimension of chi is odd, and height of this number is even, and the cohomology of base space has no true torsion, then we can improve this lower bound by 1. We can improve this lower bound by 1. So we get this one. And next we have another upper bound using this dimension of B. In this case, we assume that the dimension of P is divisible by Q minus 1, where Q is the rank of this vector bundle. We assume that dimension of B is divisible by Q minus 1. And we also assume that height of this Euler class is bounded above by this number. Then we say that the parameterized topological complexity of the sphere bundle is bounded above by this number. See, if we compare with this upper bound, we can see that the new one is better. This new upper bound is better than the old one. This one is better than the old one, and it is improved by 1, only 1. So next we have an example. Here we consider complex line bundle eta over the complex projective space, when chi is our Whitney sum of eta and trivial line bundle. So we have the dimension of this rank of this rank of this bundle chi is 3, and we see that the height of this Euler class of eta is n. And if we use the lower bound, this one, then we get that the topological complexity of this sphere bundle associated with this chi is bounded below by n plus r. Basically, here height is n, and if we choose n is even, then if n is even, then from here, this one, the 6, equation number 6, we get that the parameterized topological complexity is bounded below by height of this class plus r. And see, in this case, our q is odd. All conditions are satisfied. Q is odd, q is 3, and height is even. We assume that n is even, so height is even. And the cohomology has no torsion. So we can say that if n is even, it is bounded below by n plus r. And if n is odd, then it bounded below by n plus r minus 1. Now, if we apply the upper bound, the first upper bound, this one, then we get that it is bounded above by n plus r. We will get it is n plus r. So if n is even, we can say that the parameterized topological complexity of the associated sphere bundle is n plus r using these two. And if n is odd, then we apply this upper bound. See, we define this up. We say this upper bound is better than the old one. So we apply this upper bound. So we get the upper bound is n plus r minus 1 if n is odd. So we get the result that if we get the result that the parameterized topological complexity of this bundle of the sphere bundle associated to this bundle xi is given by this equation. When n is even, it is n plus r, and if n is odd, it is n plus r minus 1. And if we consider more general case, that is, if we consider xi L is the Whitney sum of this eta, the complex line bundle over Cpn, this eta, and L times the trivial line bundle. That means Whitney sum of this number, these bundles. In that case, we can say that the rank of this xi L is 2 plus rank of eta is 2, and each of this bundle has a rank 1. So we can say that rank of xi L is 2. Rank of xi L is 2 plus L. And if we consider L is 1, then we already discussed here. For L is 1, we already discussed here. And if we consider L is odd and L is greater than 1, then we can say that this xi has two linearly independent sections. And using our previous result, this equation number 4, if q is odd, this one, if q is odd, then it is basically r. If we apply this result, then we get, if we apply this result, then we will get the parameterized topological complexity is r. See, if L is odd, the dimension of xi L is odd. So we can apply that result. Now, if L is even, then we can say that xi L admits a complex structure. And if we apply our previous result, we can say that parameterized topological complexity is r minus 1. See, we apply this result here. If this vector bundle admits a complex structure, then the parameterized topological complexity is r minus 1. So if L is odd greater than 1, then it is r, and if L is even, it is r minus 1, and if L is 1, then it is given by this equation. That means it is larger for only L is 1. Next, we have another lower bound of the parameterized topological complexity using height of the steeple-Whitney class of this bundle. So here the result is the parametrized topological complexity of a vector bundle of a sphere of the sphere bundle associated with the vector bundle I is bounded below by this relative height plus r minus 1. Now what is this relative height? So this is the minimum number k. This height is the minimum number k such that the kth power of wq minus 1, here wq minus 1 is the q minus 1 at steeple with Nicholas, and wq is the top steeple with Nicholas of chi. So we define the relative height is the minimum number k, so that kth power of wq minus 1 does not belongs to the ideal generated by wq. That means the smallest number k such that the k plus 1th power of this wq minus 1 is belongs to the ideal generated by this q, this top steeple with Nicholas wq. Now we have another example using, we will use this result to another example. Here we consider L is the L times eta with Whitney sum with the trivial line bundle, where eta is the canonical line bundle over RPN, real projective space. Here we can check that the time rank of this bundle is L plus 1, and the total steeple with Nicholas is 1 plus alpha power L, where alpha is the generator of the first cohomology group with Z2 coefficient. It is the generator, and we can say the top steeple with Nicholas is 0 because of it admits a section. Top 1 is 0, and wq minus 1 is alpha power L. And if we consider relative height, the relative height basically the original height of this, means usual height of this wq minus 1. Since this is 0, this is basically usual height. So the height is the smallest number k such that this number is greater than n plus 1. Since the dimension of RPN is n, so and we consider alpha power L, so the height should be smallest k such that L times k plus 1, this should be n plus 1, greater than n, greater or equal n plus 1. And if we calculate this one, we get relative height is basically this number, the ceiling of this number, n plus 1 divided by L minus 1. So using our this theorem, we can say the parametrized topological complexity of this sphere bundle is bounded below by this ceiling of this number plus r minus 2. And if we apply our previous upper bound, this one, then we get upper bound. Then we get upper bound, this one, ceiling of this number plus r minus 1. That means the parametrized topological complexity of this of the sphere bundle associated with L is bounded below by this number and bounded above by this number. See, this is the difference is basically 1, not much. And here I finish my talk, and you can say this talk is based on these two articles, the first one and second one. The second one is on sphere bundle, and first one is just some result, basic result on sequential parametrized topological complexity. Hello.
Thank you.
Hello,
Are
hi.
there any questions for the speaker?
Well, yes, I have some general questions. Hello.
Hello, hi.
Go.
Hello. Thank you, Amit, for a nice talk. I was wondering if have you taken a look at considering the parametrized TC generating function associated to some family of vibrations or of vector bundles or something like that?
Now, yes, we was trying for the generating function, but we cannot means we cannot get any useful result. We are trying. We are still trying with Michael Farber.
Can I just say, in some examples which were computed explicitly, this parametrized, this generating function is obvious. I mean, a few examples which Amit mentioned at the end, not the last one, which where is a discrepancy by one, but the previous examples when the answer is explicitly given. There we can put in formal power series and see what it is, and it will satisfy this conjecture rationality as kind of expected. But Amit said already we tried some more general results, but at the moment we don't have more general results. Yes, exactly. This example is fully computed, so it is yes. I just also want to add thanks to Amit for a very nice talk.
Thank you. Can I stop sharing? Do you have any question?
Are there any further questions?
Well, I was also wondering, what about the relation of parametrized topological complexity, say, of the sphere bundle associated to the tangent bundle of a manifold and the regular TC, higher TC of the actual manifold? Would there be any obvious relation or some partial results on that direction?
Sorry, can you repeat again? I didn't understand the proper question.
So I think Jesus asks if we take a smooth manifold and its tangent bundle and look at parametrized TC of the sphere bundle associated to it, right? And the question was, are there connections between this parametrized TC and the usual TC of the manifold itself, right? Well,
exactly.
I personally don't think, well, suppose if the manifold is parallelizable, then the bundle is, trivial bundle, and this TC will be, parametrized TC will be just TC of the sphere. And, but probably there are examples when I don't, well, there could be some relationships, interesting connections, but it cannot be universal, right? It cannot be universal. It can be to a limited class of manifolds, which have kind of non-trivial tangent bundle, for example, if there are two independent sections, then we have this upper bound, very strong upper bound, and which I think coincides with lower bound. So, yeah, so if very non-trivial, I mean, I think, let's say, that's a very interesting question, and I think there must be situations, interesting situations when there is a connection, but it cannot be universal.
Sure. Okay. This was kind of motivated by the fact that, well, in the case, for instance, of real projective spaces, tangent bundles are related to multiple of the canonical line bundle, of the Hopf bundle. So it might be interesting to study then a variation of what I asked in terms of precisely a generalized vector field problem, namely multiples of the line bundle, and seeing what happened for the parametrized TC of those things.
Yes, it's a good question. Actually, it's a very good question. In fact, what we are trying with Amit at the moment is somehow related to this, but not exactly that. Yes, it's a very good question. Thank you, Jesus.
Thank you.
Yeah, I'm going to go ahead and stop the recording now. If there are additional questions, please feel free. Before I stop, let's thank the speaker one more time.
Thank you. Thanks, Daniel.